Okay, let's look at another example problem. It appears simple, but this is as complicated and as apparently nasty as it gets. So I want to tackle a pretty, it's not difficult, but it appears difficult. So I don't want you to be deterred. It's not difficult. It's a pretty simple problem if you think about it. If you go from step one to step two to step three, if you take one step at a time, it's a really simple problem. Okay. However, there is a lot of mathematical manipulations, algebraic manipulations, but we just have to keep our analysis straight, our calculations not mixed up from step A to step B to step three, C. Okay, so let's see. The problem says, given Vg value is 250 cosine 1000 t volts. Now there is a variable capacitance here, a variable cap is adjusted until the current is in phase with the voltage. That's something we have to understand what it means. Okay, cap is adjusted until the current is in phase with the voltage. Okay, what it simply means is what it means is that the circuit appears purely resistive. Okay, so let's begin there. Actually, solution. When the current is in phase with voltage, what it means is this implies that the circuit is purely resistive. What it simply means is the impedance, if you look at the imaginary part of the impedance, that equals zero. Okay, the imaginary part of the equivalent impedance is essentially zero. And we are going to use this later on. But for now, park this knowledge to one side of the mind. Okay. So at the frequency of the input, find a value of the capacitance such that the complex impedances cancel out each other. Okay. First, what we are going to do is to leave all the impedances, all the resistance, capacitance, and all of these in their symbolic form. Okay, so I'm going to call this as L actually. Okay, I'm going to call this as R, and I'm going to leave this as C. Okay, and I'm going to solve using these variables L, C, and R so that I can keep it general, so that I can apply this kind of result to other circuits with the same structure but different values. Okay, now what we want to notice really is that if you think about it, there is two resistances here. There is two impedances here. There is one impedance ZL, okay, there, and there is another impedance here, which is the equivalent of these two. Okay, let's call this, I don't know, I'll call this Z prime. Okay, where Z prime is simply C in parallel with R. Okay, or J omega C, ZC. Okay, the impedance of the capacitance in parallel with the resistance. Now, this guy ZL is in series with Z prime. Okay, therefore, the equivalent, Z equivalent of all of this circuit, all of this equivalent impedance is simply ZL plus Z prime. Okay, that said, let's write the expression for ZL then. ZL is pretty straightforward, J omega L. We know the value of L because it's given to be 5 Henry. We know the value of L, omega, don't we? We do know the omega value, but for now we are not going to substitute. We'll just leave it as is. Okay. Then let us find Z C. What is ZC? Okay, ZC is 1 over J omega C. Right? We know 1 over J omega C. Now Z prime is simply ZC in parallel with R. Okay, ZC in parallel with R, which is simply R times ZC by R plus ZC. Remember, if you have two resistances R1 in parallel with R2, the equivalent is R1 R2 by R1 plus R2. That is simply the equivalent of two parallel resistances. That's what I'm using here. R times ZC by R plus ZC. So we can write it as, if we divide the numerator and denominator by ZC, I have R by 1 plus R by ZC. Okay, simply cancel out the ZC on the numerator and denominator side by just dividing by ZC. Okay, I have not done anything here besides just dividing the numerator and denominator by ZC. Okay, so this is Z prime value. Okay, now once we know Z prime, Z equivalent is simply ZL plus Z prime. Remember, ZL is this guy, Z prime is this guy. Add them both because they're in series. So what you have is ZL plus R by 1 plus R by ZC. Okay, there's no more circuit analysis here. We are simply doing mathematical jugglery at this point. Okay, Z equivalent is ZL plus R by 1 plus R by ZC. Now, we can do the symbolic equation, symbolic manipulation here. So the Z equivalent is multiply the whole damn thing by 1 plus uh, R by ZC, or taking this as the least common multiplier. We have um, Z times 1 plus R by ZC, okay, by 1 plus R by ZC plus R by ZC plus R by 1 plus ZC. Okay, R by 1 plus R by ZC. Okay, all I have done is to take the least common multiplier or just multiply this ZL by this term on the numerator and the denominator. I have not done anything. I have just simply done a mathematical jugglery. Now what I can do is to factor out this guy in common. So Z equivalent equals to 1 plus R by ZC. That's the common denominator. Z into 1 plus R by ZC plus R. So this R is coming from here, okay? And this guy is coming from here, okay? So just the denominator is factored out, okay? Now that's the Z equivalent, Z plus ZRL. This is again ZL, right? ZL. All of this is ZL. So let me expand this a little bit more. Z equivalent equals to ZL plus ZL times R by RZC plus R, the whole thing divided by 1 plus R by ZC. Okay, so all I'm doing is doing mathematical jugglery here. Um, Now, another piece of jugglery that I can do is noticing that the denominator here, I want to get rid of the imaginary terms from the denominator. So what I do is to multiply both the numerator and the denominator by the complex conjugate of the denominator. Okay, so what do I mean by that? I have this guy to begin with, ZL plus ZL times R by ZC plus R divided by 1 plus R by ZC. So all I'm doing is multiplying the numerator and denominator by the complex conjugate of the denominator, 1 minus R by ZC. The denominator is 1 plus R by ZC. Its complex conjugate is 1 minus R by ZC. Okay. Then what we are left with is and some more simplification. So all of this is Z equivalent. Okay. I want to solve this problem because it's a lengthy problem. However, it's a straightforward problem. Okay. So Z equivalent is really the multiplication of all of this. Now, let's see if we can simplify this a little bit more. It gets ugly before it gets better. So watch out. So the denominator 1 plus R by ZC multiplied by 1 minus R by ZC, it gives you 1 minus R by ZC the whole square. So 1 minus R by ZC the whole squared. Okay, simply put, a plus b into a minus b is a squared minus b squared. Now let's multiply the numerators. Z plus z l r by zc plus r multiplied by 1 minus r by zc. Okay, let's see. Now what I have here is, you see, multiply this one with all of these terms. You have z, so pay attention, all of these multiplied by 1 will give you what? The same thing. Okay, I might actually copy this and paste it, duplicate it. Okay, that's coming from the multiplication with 1. Now there's also multiplication with this guy. Okay, with r by zc, when you multiply each of these terms with all of this, what you get is the following. You see, like I said, pay attention. It's going to get a little interesting. So R times ZL. So the first step is that noticing that this factor R over ZC multiplies this term ZL. So I have R times ZL divided by ZC, right? Plus the same term multiplying this guy. Okay, so that becomes R squared ZL divided by ZC. Okay, R times a ZC squared. Okay, that's the second term. Okay, the third term is simply the multiplication of these two, which is R squared by ZC. Okay, r squared by zc. So that's simply algebraic manipulation we are looking at right now. Okay, this is all z equivalent. Okay, everybody with me? Now we can simplify this. All of this, believe it or not, simply comes down to a lot of these cancels actually. If you see ZL R by ZC cancels negative ZL R by ZC, and then you will be left with simpler problem, simpler expression. Z equivalent is the denominator is simply 1 minus r by zc the whole squared, 1 minus r by zc squared. So zl, okay, minus r squared by r squared zl by zc squared by zc squared, okay, by zc squared, r squared zl by zc squared. So that's this term plus or negative r squared by zc, okay, plus r. Okay, so we have this guy. The circuit will appear. So if you think about it, there is this numerator term, there is this denominator term. The circuit will, now we are going to come back to the other piece of information that's given to us, okay, which is to say that the circuit is purely resistive, or that Ig is in phase with Vg. Now we are going to apply that. When the circuit is purely resistive, when the circuit is purely resistive, when the circuit is purely resistive, you see the numerator ZL minus R squared ZL by Z squared, ZC squared, minus R squared by ZC plus R. All of this, if you take the imaginary part of it, that should equal 0. Okay? Let me go back. That's exactly what I said. That's what I defined. The imaginary part of the impedance is really 0. That's what I'm showing here. That's what I'm doing here. The imaginary part of the numerator should equals to 0. Okay, so let's simplify this a little bit more. Let's start with the numerator, which is the ZL minus r squared ZL by ZC squared, okay, minus r squared by ZC plus R. Okay, so that's the numerator. Let's try to separate this into the real part and imaginary part. So I'm going to write this guy ZL as J omega L. Okay, and then I'm going to write out each of these terms. The second term, this guy, I'm going to write as negative r squared times j omega L divided by negative j by omega C the whole squared. Right? ZC is what? ZC is 1 over j omega C, and which is the same as negative j by omega C the whole squared, because there is ZC squared. So I'm simply writing out the impedances using the j term. Okay. Now let me write this next one as well, which is this guy, negative r squared by negative j by omega c. Okay, that's the idea. And then there is this term, r term over here, the boring r term. Okay, now let me um, simplify this further, and you will see where I'm going with this. I'll take the r out, okay, plus j omega L, that's coming from here, R is coming from there, right? R plus j omega L, okay, minus R squared times omega L by j into negative 1 over omega c the whole square. So I have cancelled j once, and another 1j in the denominator cancels the j in the denominator. Remember, j square equals to negative 1. Okay, now there's that part. Then there is, don't forget the component coming from here, which is r squared by j by omega c. Okay, you see this j, the negative here cancels the negative there. Okay, so this is all the numerator. Okay, the numerator. Let's simplify this a little bit more, or maybe you know what? This is the real part. All of this is the imaginary part. That is what we are after. Remember, we are looking at the imaginary part of this numerator and equating that to zero. So let's do that. J omega L minus R squared omega L by j into negative 1 by omega c the whole squared, okay, plus r squared by j into 1 over omega c, okay, all of this equals 0. The imaginary part of the numerator, where the numerator is this guy, all of this guy, okay, the imaginary part is equated to 0. That's all I have done here. Okay, so now we set the complex impedances all equals to 0. Okay, so negative j omega L. I can play around with this a little bit more. J omega L comes out to be j omega L. Okay, negative r squared omega L divided by negative 1 over omega c the whole squared. Now you see 1 over j is what I have here, 1 over j. I'm going to write it as negative j, okay? Because 1 over j is, I can write it as j squared, which is negative 1 multiplied by negative over j. So I have negative j equals to 1 over j, okay? Because j squared equals to negative 1. So I have simply taken the j to the numerator side. The same here as well. Plus this 1 over j, I'm going to write this as negative j. The rest is all r squared by 1 over omega c. All of this equals 0. Okay. Now I'm at a point where I can factor out j. Okay. J omega L plus r squared omega L by 1 over omega c the whole squared. And I can throw in the negative there, but it doesn't matter because we are squaring it. Negative r squared by 1 over omega c. Okay, what I can do really is equate all of this to 0. Okay, because all of this should be 0, meaning that this term should equal 0, omega squared. We can rearrange this last result a little bit more, and we'll see that omega L plus r squared omega L by 1 over omega squared c squared minus r squared by 1 over omega c. All of this equals 0. Okay, simply I can rearrange this some more, omega L plus r squared into omega L into omega squared c squared. So all I'm doing that is denominator within the denominator and take it to the numerator. Okay, minus r squared omega c, all of this equals to 0. Okay, the last result from the quadratic expression. Okay, um, all of this equals to 0. Now you see, think about this. If you think of this c as your variable, then you have all of this ax squared plus this is bx, which includes the negative sign, plus c. Okay, so this really is a quadratic in C. We are getting somewhere here. You see, this is written as ax squared plus bx plus c. Okay, we can plug in the value because we know omega value, we know L value, we know R, just about everything. The only unknown is C. Okay, so I can plug in those numbers and we gradually get to, we are very close to getting to what it is that we want. Okay, so I can factor out C squared and omega R squared L omega squared. Okay, R squared L omega squared, that's the quadratic. Okay, R squared L omega squared. And we can actually throw out, see, you can throw out a factor of omega L. Okay, because omega L is common through all of these. Okay, minus RC squared. Excuse me on that. But the idea is we can find a quadratic. We're going to write a quadratic in C. So we can substitute all of this to be, we can factor out omega. Certainly we can factor out omega because omega term is common. We can factor out that guy. Okay. So I'm going to write with c squared as common, r squared L times omega squared. So this one is factored out, that one is thrown away because it's common in all the terms. R squared L omega squared plus, I can factor out a c here, negative r squared, and this omega cancel, right? This omega cancel along with this guy. Okay, plus, let's not forget this L over here. Okay, plus L, that's the quadratic. Now I can plug in C squared into, plug in the value of R, 12.5 kilo ohms, multiplied by 5 Henry, multiplied by 1000 radians per second. You see, that value of Z is, that value of omega is given to be 1000 radians per second. Okay, 1000 radians per second plus P times negative 12.5 kilo ohm, the whole squared. Okay, and then 5, that's the L value, 5 Henry, all of that equals to 0. So you can, do the math, you'll get up with C, you'll get something like C squared, 7.81 e to the 14, or 7.81 into 10 to the 14, plus C into negative 1.56 e to the 8 plus 5 equals to 0. So you really have ax squared plus bx plus c equals to 0. Now you can find a solution. Okay, minus b plus or minus square root of b squared minus 4ac by 2a, minus b plus or minus root of b squared minus 4ac by 2a. That's the solution for a quadratic expression ax squared plus bx plus c. You will get the value of c to be there's a minus B plus or minus term. So you'll get a value of C to be um, roots. It has two roots, 1.0.160 microfarads, or it has a value of 0.04 microfarad. Okay, so from the problem statement, you'll see that you want to pick a value of Z, assume something that's greater than 40 nanofarads. Okay, this one is not. Of the two solutions you have here, this one does not meet the criteria. So C equals to 0.160 microfarads. So this is the answer. What did we do? A whole lot of crap of mathematics. Besides mathematics, there is nothing else we did. All we did was to notice that in the capacitance, when you keep adjusting this, at some point, the imaginary part, that is the combination of the capacitance and inductance, that equals zero, and the overall impedance, it has only real part. It has no imaginary part. So I equated the imaginary part. Okay, simply series and parallel combination, finding the imaginary part, equating the imaginary part to zero, then you'll get a quadratic expression in C, which looks like this. Okay, the quadratic expression in C looks like that. Okay, now once you have the quadratic expression in C, what you can do is to find the solution for C and find the best answer that fits the solution. Okay, there we have it. A pretty lengthy process. However, it's simple enough. Okay, to the point where the circuit analysis involved is simple. Okay, that's one part. The other part is what is the overall Z? We are supposed to calculate the overall Z. So I'm not going to solve the entire value for problem number B. What is the overall Z? If you remember the Z or Z equivalent, what is the value of that? Z equivalent equals to ZL plus Z prime, right? Let me go back. Somewhere here, I have shown that the overall impedance is the sum of this inductance and the Z prime. Okay, when I add those two, and then I can plug in the values for ZL. No, I think I kind of did this math already. ZL equals to J omega L. Z prime equals to R times ZC by R plus ZC. Remember, there is this capacitance in parallel with the resistance, and then which is in series with the impedance L, C, and then R. Okay. Now, you know all the variables here. You know the value of J omega L. You know the value of omega. You know the value of um, L. And then you know the value of R. ZC. What is ZC? ZC equals to 1 over J omega C. Okay, 1 over J times omega C. Okay, 1 over J times omega C. So you plug in those values and find ZC plus Z prime, which gives you the equivalent. Once you do that, you will see that Z equivalent magically turns out to be 2500 ohms. And why is this very interesting? Because think about it, the impedance only has a purely resistive term. There is no J term. Okay, where is this imaginary part? That's not there because that's what we kind of assumed, and that's what the idea is when the circuit is purely resistive or when the current and voltage are in phase, the overall impedance is just resistive. Okay, so a pretty lengthy problem. Watch it over and over again. Besides mathematical manipulation, there's not a whole lot of new concepts in here. Okay.